we are going to continue with our problem set. We are dealing with question 8 today, and if you haven't seen the other questions, I'm going to link them above so you can take a look at that. So in this video, we are looking at an integral, a definite integral. So we want to compute the integral from 0 to 1 of x squared sine of x cubed plus 1 dx. So the question says that use substitution. So this is a good hint. Now, what is going to guide you to use substitution, or what is going to be your substitution? So we are going to use u substitution, but before using u substitution, we have to know that the derivative with respect to x of x cubed is 3x squared. So this whole idea will guide us to know that our u substitution should be x cubed plus 1. This is very important. You need to know that your u substitution is this, and once you're able to identify correctly your u substitution, every other thing becomes simple. So you can look for your du. This will be 3x squared dx. And if you look at it critically, this is x squared and this is dx, and this is x squared, this is dx. So you can replace that with du on 3. But I'm not going to do that. I will go directly. So I'll look for dx, right? Remember, we're doing substitution. So my dx will be simply du all over 3x squared. So we can go ahead and call this equation 1, right? Equation star, and we call this equation 1. Now it's very important to number the equations. So if we take equation 1 and substitute in our equation star, we are going to get the integral from 0 to 1 of x squared sine of, we already saw that this is u, so this will be u, and our dx is du all over 3x squared. We notice that x squared is going to cancel with x squared, and everything is in terms of u. So if we continue, we're going to have the integral from 0 to 1 of 1/3, since it's a constant, sine of u du. And simply, when you integrate sine, you have negative cos, so negative 1/3 cos of u, from 0 to 1. So that is our computation. And remember, you have to substitute your original variables for u. So this is equivalent to negative 1/3. The cos of u is x cubed plus 1, and our upper limit is 1, and our lower bound is 0. So we'll go ahead and substitute the values. So we're going to have upper limit will be cos of 2 minus lower limit cos of 1. So we notice this is, remember, is 1/3, remember. So 1/3 cos squared plus 1/3 cos of 1. That's our result. So this can be factorized as cos of 1 minus cos of 2. So we're now going to compare this with our options, and we notice that option A says that 1/3 cos of 1 minus 1, this is wrong. Option B, there is no 1/3, is wrong. Option C says 1/3 cos of 1 minus cos 2, which is exactly what we have here. So this is our correct option. So option C is the correct option here. So this is our correct option, and option D definitely wrong. So that is it for this question set. We're going to move on to the next question. So the next question says that what is the solution to the differential equation? So we have been given a simple differential equation, and this is dy all over dt to be equal to y plus 1 with initial conditions y of 0 equal to 1. So it's very important to know these initial conditions, because they are going to help us to get our value of the constant k or c or whatever constant you've chosen. So we'll name this as equation star, and our function is in terms of t. We can look at it from here. So this is something, it can be written as y of t equal to 1. So this means t is 0 and y is 1. This is very important. You have to keep this in mind. Now, we have been given a simple differential equation, and to solve this, we're going to go by separable variables, right? So we're going to try to bring all the variables in terms of y on one side and all the variables in terms of t on the other side. So doing that, we're going to have dy all over. We notice that this all is in terms of y because 1 is a constant. So this will be y plus 1. So we have to take everything from the right hand side. We divide we basically you're dividing all through by y plus 1. So this will be equal to, and multiplying all through by dt. So if we notice this, we have actually simplified it. We have separated our variables, all the variables in terms of y are on the left hand side and all the variables in terms of t are on the right hand side. So we are going to go ahead and take our integral. So we're going to be integrating this. So taking the integral, we have y plus 1 to be equals to the integral of dt. So we know, right, from basic integrals that the integral, you need to know this, that the integral of 1 all over x dx is the ln of x, right? So when you look for the derivative of the denominator, if it gives you the numerator, then that integral is simply the ln of the denominator. And it's the same thing here because on the numerator we have 1, and to get if we use our u substitution, which is the longer method to do, you're going to notice that the derivative of y plus 1, which is in the numerator, so this will simply be the ln of y plus 1 to be equals to the integral of dt is t now plus our constant k. So from here you can use your initial values to get your value of k, and you substitute here. So we're going to call this our equation 1 or equation double star depending on you. So we're going to substitute. Now I'm looking for the value of k. That's the step, looking for the value of k, right? The value of k, we have the ln of what is y is 1, so 1 plus 1 will simply be 2 to be equals to t is 0, so this is k. So we know that this is our value of k. We can call this value 2, and we say substituting 2 in equation 1, we're going to have, let me create some space, then we're going to have the ln of y plus 1 to be equals to t plus the ln of 2. There are many ways to solve this. So we want our function to be in the terms in the form y of a function equals to, if we look at the options given to us, you see the functions are all in terms of y of t equals to something. So there is no ln and there is no constant k. That's why we had to look for those values. So basically we want to make y subject of formula here. So we're going to take the inverse natural logarithm. We know that e to the ln of x should be x. This is a theorem, or a law you should know when dealing with logarithmic functions. So in this case, we're going to take inverse log on both sides. So it will be y plus 1 to be e to the power t plus ln of 2. Remember, from basic laws of indices, we have a raised to the power x multiplied by a raised to the power y. We can write this as a raised to the power x plus y. And this is also, opposite, meaning that if we have a raised to the power x plus y, we can write this as a raised to the power x multiplied by a raised to the power y. Basic laws of indices, since they have the same base. So we already saw from here, right? This will simply give us y plus 1. That's our answer for the left hand side. And this, we can write this as e to the power t multiplied by e to the power ln of 2. Again, applying this, we notice that this is going to be 2. So y plus 1 will simply be 2 e to the power t. Simple. So we want to look for y. So y will be 2 e to the power t minus 1. And since our function is in terms of t, we can safely write it as y of t, like this, y of t equals to 2 e to the power t minus 1. And that is our solution. So comparing this with the options given to us, we're going to know the correct answer. So the first one says y of t equals to 2 e to the power t minus 1. I guess that's the correct option. So This is correct. The second one, this is not correct. And the third one, y of t equals to 2e to the t squared. T squared, that's not correct. Y of t equals to, now this is out of range. Wrong, wrong. So let's move on to the next one. So this question is dealing with properties of matrices, specifically matrix multiplication, and we have been told that we have three matrices, A, B, and C, and A is an n by m matrix, B is an n by m matrix, C is an n by r matrix, with n different from m, different from r, and they're all positive integers. Now, which of the following options are correct? So which of the following computations are possible if A is that, right? So what do we know? For two matrices to be compatible, for them to multiply each other, the number we have, let's take for instance this, right? Let's say if we have a matrix, a 3 by 3 matrix, and I'll use m and n since our example above. Let me use m here and n here. Let's say we have 3 by 2. Yes, let's take this example. What do we notice? This is the number of rows here. There are 3 rows, 3 columns. There are 3 rows, 3 columns, and here there are 3 rows, 2 columns. So for it to be compatible, the number of columns from the first matrix should be equal to the number of rows from the second matrix. So 3 columns equals to 3 rows. This is compatible, and it is very easy to see when you write down the dimensions of the matrix, right? So if you write in that this is a 3 by 3 matrix and you write this is a 3 by 2, you can easily look at this. Once these values are the same, then the matrix is compatible. If they are not the same, then it is not compatible. Now, when you compute this matrix, you're going to get a 3 by 2 matrix. And how do I get that? You simply get this. That will be a 3 by 2 matrix if you compute, like if you finalize with your computation. So we're going to use this idea to select our options here, and to do that we're going to start with option A. Option A is here. We're going to use the options to select, right? That's the instruction. So A says that A multiply with B. What do we know? A is an n by m matrix and B is an n by m matrix. Look at it. So the number of columns from the first row is different from the number of rows from the second. So this is not compatible. This is not possible. So it's not possible. This is not compatible. You can't do this multiplication. So option A is not possible. It's not possible. Now option B says A, B transpose C. Remember, here B transpose would simply be an m by n matrix. So in this case, what you can do is to simply compute this, then you compute that, right? So you compute this, you have a matrix. You compute this, you take the result of that computation, you compute with C, and then you're going to have your resulting matrix. Now let's look at them individually. So we're going to consider just A with multiply with B transpose. A is an n by m matrix and B transpose is an m by n matrix. Again, we see that the number of columns from the first one is the same as the number of rows from the second one. So this is possible, right, for the first part. And our result is going to be an n by n. So this is an n by n. So this will give us an n by n. Now we want to compute this with C. And what is our C? Our C is n by r. Again, what is our result? This is compatible. Another way in which this question can be framed is simply by stating that what is the result of the computation A multiply with B transpose with C, and that will be your result. This will be the answer. Now option C says that what is the computation of A C transpose? Again, C transpose here is n by n, n by r by n. So if we look at the computation, A is an n by m matrix and C is an r by n matrix. So this is not compatible. So this is not possible. That is not possible. And again, D says A with C with B. We already saw that A and C are not compatible, right? A and C are not compatible because we have M here and N here. So these ones, just these two are not compatible. Everything will not be compatible. So that's wrong. CA, the next one is CA, CIA. Anyways, the next one is CA, and C is an N by R matrix, and A is an N by M matrix. Again, these they are not compatible. So this is wrong. And the last one, the last option is A to the power T C, and A transpose here, A transpose is M by N. So looking at this, what do we notice? A is an M by N matrix and C is an N by R matrix. Again, they're compatible and the result is an N by R matrix. So this option is possible. So these were the only two options and the remaining are not possible. So the next question is matrix computation. We have been asked to find the inverse of A. Now there are certain properties we need to know when computing, when dealing with the inverse of matrix. We know that if you multiply a matrix with its inverse, then you're going to get the identity matrix. And if you multiply the identity matrix with any matrix, it's going to give you that matrix, meaning the identity matrix with the inverse will give you the inverse. So these are very interesting properties we need to know. And once you have this in mind, you can easily compute the inverse of the matrix. So there are many ways to compute the inverse. You can get the determinant, you take 1 over determinant times the adjoint of the matrix, but that is a very long method. So the best method to use is usually the row echelon or the row reduced form. And what does the row reduced form say? Let's say if we have a matrix, let me just create some space and put this somewhere there. So we have our matrix A to be 0 1 negative 1 and 1 0 1 2 2 1. This is our matrix A. Then to get, as we saw earlier, if we have a matrix A, right, and at one point we do the computation, let me write this way instead. Let's write this 1 0 0 0 1 0 0 0 1. So this is the identity matrix. We saw that A multiplied with I will give us A, right? Definitely. Now we want to get the inverse. So if we multiply all through by the inverse element, we're going to have A inverse multiply with A and multiply with I equals to A inverse multiply with A, right? What do we notice? A multiplied with A inverse from here is I, and this will be multiplied with I equal to, and A inverse multiplied with A will give us I as well. What do we know? I multiplied with I will give us I, and this will be I, the identity matrix. So this is true. So meaning that if we're able to do a computation or carry out a computation with this matrix such that we get our identity matrix, whatever is going to be here will be the inverse, right? From here, it's simply going to be the inverse. So that is the whole idea behind this, right? That's the whole idea. And having that in mind, we're going to use the row echelon form to get the inverse of that matrix. And to do that, we simply want at the end to have something like 1 0 0 0 1 0 0 0 1, and then computed with something here. We don't need a value, right? We're going to get certain values here, and that will be our inverse. So based on the operation that we're going to do to transform our matrix A to the identity matrix, that operations is going to provide or produce the inverse matrix this other way. So you have to understand it that way, and we are just going to proceed with the calculations. So using the row echelon form, let's start computing. So the easiest way to do this is always to first of all write down all the rows that are going to be unchangeable, right? all the rows that are going to remain constant. And to do that, we decide which one you want to put as 0 first. So let's say we want a 0 here, right? Let's say we want a 0 here. If you want a 0 here, what are you going to do to have a 0 here? In fact, let's start with it very simple. 1 is 0 here, because I see if we add these two, it's going to give us a 0, meaning that this and this is going to remain constant. So the first thing I need to do is just to write down all the elements that are going to remain constant. This will be 0, 1, 0, 0, 0, 1. Now remember, we're adding this and this, right? Remember, top and bottom, top, bottom. So adding that, 0 and 1 will give us 1. 1 and 0 will give us 1. Negative 1 and then 1 will give us 0. 1 and 0 will give us 1. 0 and 1 will give us 1. 0 and 0 will give us 0. So we have had 0 here, right? We are satisfied with that. Now, what do we notice? Let's say, you have to really be vigilant when computing. We notice that there is a 2 and a 2 here, and there is a 1 and a 1 here, meaning that if we multiply the first row by 2 and we subtract from the third row, we are going to get 0 and 0 here. Remember, we want here to be 0, here to be 0, here 0, 0, 0, right? That's our main goal. So the sooner you can do that, or the quicker you can do that, the better for you. So we are going to multiply this by 2, right, and subtract here. So what is changing? Actually, this is changing, right? So as I said earlier, you have to write all the elements, or all the elements that remain unchanged. So the first row is going to remain unchanged, and we have 1, 1, 0, 1, 0, 1, 0, 1, 0. Again, we're multiplying here by 2, so multiplying and subtracting. So 2 minus 2 will give us 0 here. 2 minus 2 will give us 0 here. 2 times 0 is 0, minus 1 will give us minus 1 here. 2 here minus 0 is going to give us 2. 2 here minus 0 is going to give us 2. And here is going to give us minus 1. We notice that there's a 0 here, 0 here, 0 here, right? Let's say we want a 0 here, right? We want a 0 here. What are we going to do? We can take this subtracted with this. So meaning that this will remain, this is changing, right? And the first and the third rows are constant. So if we continue, we're going to see that 1, 1, 0, 1, 1, 0, and the other one is 0, 0, negative 1, 2, 2, negative 1. So what are we doing? We're subtracting the first minus the second, right? 1 minus 1 will give us 0. 1 minus 0 will give us 1. 0 minus 1 will give us minus 1. 1 minus 0 will give us 1. 1 minus 1 will give us 0. 0 minus 0 will give us 0. Good. So we're gradually getting to the result. We want a 0 here, right? We want a 0 here as well, right? So how can we do that? We can use the second and the third. And how can we, so meaning that the middle row is changing, right? We'll just repeat the other ones that are not changing. And we have 1, 1, 0, and here we have 0, 0, negative 1, 2, 2, negative 1. So we're subtracting, we're using this and this, right? That's what we're going to use. So we basically take this minus this. So R3 minus R2, right, will give us our R2 prime. That's the formula. So we are going the reverse way. So 0 minus 0 will give us 0. 0 minus 1 will give us minus 1. Negative 1 minus minus, right? So it will be 0, which is what we wanted, right? Which is what we wanted. And here we are going to have 2 minus 1 will give us 1. 2 minus 0 will give us 2. Negative 1 minus 0 will give us negative 1. And finally, we want a 0 here. We want a 0 here. How can we get a 0 there? We can use this and this, right? We can use this and this to get, we can use this to get a 0 there. So meaning this and this are constant. They're not changing. So we're going to repeat that. We just write 0, negative 1, 0, right? 1, 2, negative 1, 0, 0, negative 1, 2, 2, negative 1. So We 1 is 0 here. We basically add this and this, right? So 1 plus 0 will give us 1. 1 plus minus 1 give us 0. 0 plus 0 give us 0. This plus this will give us 2. 1 plus 2 will give us 3. And this will give us minus 1. So we have had ones, all ones on the diagonal except the negative. So we can simply multiply all through by negative and we'll have our original value. So meaning that if we here is already okay. So we have this. Here we multiply by negative. We're going to have 0, 1, 0. And we had 2, 3, negative 1. So multiplying by negative, we're going to have negative 1, negative 2, and 1. Multiplying also here by negative, we're going to have 1 here, and here will be negative 2, negative 2, and 1. So basically, this is our identity matrix, and this is our inverse. So you have to compare your result with this. So looking at the options, we have 2, 3, negative 1. We just check for 2, 3, negative 1. We have 2. No, this is already out because, 2, 3, negative 1. It seems like what we had, negative 1. So we have negative 1, negative 2, 1. So negative 1, negative 2, 1, right? And the last one, negative 2, negative 2, 1. Negative 2, negative 2, 1. So that is our inverse. So this is our inverse, and every other thing is going to be wrong. Now there is this approach you can use. So if you notice from these identities that I said earlier, right, you can decide to go directly. If you know how to do your matrix multiplication very well, you simply take the matrix A, you multiply with the inverse, right? If it gives you the identity matrix, then that is your result. If it gives you any other matrix, you just move on to the next option and you verify. Instead of going through all of these row echelon form, which you can likely make a mistake. If you are good at multiplying matrices, you should use that method. So just do your multiplication normally. So that's it for this question, and we'll move on to the next one. So the next question says that what is the cross product between U and V? So we have been given our U to be 2, negative 3, 1, all that transpose, and our V to be 1, 4, 5, all that transpose, right? So you can rewrite this as 2, 3, negative 3, 1. That will still be your U in vector form, and this will be 1, 4, 5. But for this question, we don't need it in this format. That's why it was given to us in the transpose format. So to compute our cross product, we need a 3 by 3 matrix, right? And this matrix is supposed to be all in terms ij and k, right? So we know our elements ij and k, and we know from the determinant of matrices, if we put this aside, we're going to have, let's say is U, right? We're starting with U, so we have 2 here, minus 3, 1, right? 2 minus 3, 1, correct? And 1, 4, 5. So we also have to have in mind that for matrix, for determinant of matrix, there is this polarity, should I say matrix, we need to consider. So whenever we're doing looking for the determinant, right, we need to know that each of these elements they have these polarities. So when computing that element, the sub determinant of that matrix will be negative for the second row, positive for the first row, positive for the first row, first column, and so on. So we have to know this. So having that in mind, we're going to start with I, which is positive. So you can basically write it as I, and the sub determinant here, right, is just like covering this and this. We're left with minus 3, 1, and 4, 5 to get a determinant. So we are done with that. We go on to J, right? This is our J. So J, remember, is negative, so it's negative J. The determinant of 2, the sub matrix is 2, 1, 1, 5. And we move on to the next one, K. We move on to the next one, K, right? And K is positive plus K, and we have 2, negative 3, 1, 4. So that's it. We have that. And we have to look for this is generally to look for the cross product. We use this method, right? And let me try to clean this up. Good. So we are going to look for this is the determinant of 2 by 2 matrix. So it's simply negative 3 times this will be I into negative 15 minus 4 minus j into 10 minus 1 plus k into 8 minus 3, right? So we further simplify that, we're going to have this will give us negative 19, I believe, and this will give us minus 9j, I believe, plus that is 11k. Now let's compare that with our result. If that is a product, we have negative 19 minus 9 and 11 somewhere. Yep, and 11. So this is our correct answer. I should take that instead. So this is wrong. Good. And let's move on to the next question. So we have some curve sketching here, and we've been asked to look for compute. So this is a more written question, not MCQ, where you have to select. Here you have to like show your working, and to compute this we have to do solving like detailedly. And to do that, the first part says that what is the domain of the function. So this is curve sketching, and we know to sketch a curve, I have this acronym called the Ladvis, which is the domain, the limit, the asymptote, the turning point, the variation table, the intercept, and the slope or sketch. The sketch actually it is. So using this, first of all, we have been asked to look for the domain, which is D. So to look for the domain of definition of any function, it's simply the range in which that function exists, right? So we have our function f of x to be 3x squared minus 1 all over x squared minus 1. So the domain will simply be all set of real numbers except when the denominator, or except when x squared minus 1 is different from 0, meaning that when x is different from plus or minus 1. So the function f of x exists on the set of real numbers except when x is at 1 and negative 1. That is the option for A. Option B says that what are the intercept with the x-axis. So to get the y-intercept occurs, right? We need to know this. This is option B, this is A, right? The y-intercept occurs when x is 0. So meaning that our f of x is y, right? So meaning that our y, we are simply going to look for f of 0. So y, right, will be equals to 3 into 0 squared minus 1 all over 0 squared minus 1. So this will be negative 1 all over negative 1, which will be 1. So our intercept y is equal to 1. That's our intercept. The line actually is y equals to 1, and the intercept, which is a point, right? The point at the intercept is 0, 1. We need to know this. So meaning that our graph is going to pass through this point 0 and 1. Again, to get the x-intercept, right? The x-intercept occurs when y is 0, meaning that our f of x is 0. So know that our f of x is 3x squared minus 1 all over x squared minus 1. So this will be 0. So meaning that 3x squared minus 1 is 0. 3x squared will be 1. So if you continue, x squared will be 1/3, and x will be plus or minus the square root 1 over the square root of 3. So we're going to have two intercepts here. So we have 1 on root 3 comma 0, and another intercept at the point 1 on negative 1 on root 3 and 0. Our graph is going to pass through this point, this, and this other point. So option C says that what are the horizontal asymptotes. Now There's a definition to get a horizontal asymptote. C says a horizontal asymptote. The horizontal asymptote is simply the limit as x tends towards infinity of our function f of x. If this happens to be a, then y equals to a is our horizontal asymptote. So we know our f of x is, so we are simply going to look for the limit as x tends to infinity of 3x squared minus 1 all over x squared minus 1. So this is a very simple limit because the degree of the numerator and the denominator are the same. So basically we can factor out x squared. We'll be left with 3 minus 1 all over x squared, right, all over x squared into 1 minus 1 all over x squared. So this is the limit as x tends to infinity. We know that the limit as x tends to infinity of 1 on x is 0, right? Meaning that 1 all over infinity is 0. You need to know this. So this we have that. So having this in mind, we know this can easily cancel out. So this will cancel out, and if we insert our limit, we notice that this will give us 0, right, from here, and this will give us 0. So it will be 3 minus 0, which will be 3, and down here will be 1 minus 0, which will be 1. So this will be 3. So meaning that y equals to 3 is our horizontal asymptote. So that's it. Definitely the next question is, what is the vertical asymptote? So the next one is, what is the vertical asymptote? So to get the vertical asymptote, we already saw from the domain, right? So the vertical asymptote is simply x squared, that's d, is x squared minus 1 should be equal to 0. It occurs when the function does, then when the denominator approaches to 0. That is when the function tends to infinity, the function itself tends to infinity. Or when the denominator, right, this is our denominator, if this denominator is 0, it's going to give us all the vertical asymptotes. So this is x minus 1, x plus 1 equal to 0. So x will be 1 and x will be minus 1. So these are the two vertical asymptotes. Now the next one says that compute and analyze the first derivative of our function. So to compute the first derivative of our function, e, right, e says that f of x, which is y, to be equal to 3x squared minus 1 all over x squared minus 1. So to get our first derivative, y bar, so this is a quotient, we're going to use the quotient rule, which is the bottom x squared minus 1. The derivative of the top is 6x minus the top 3x squared minus 1 multiplied with the derivative of the bottom 2x all over the bottom square x squared minus 1, all that squared. So we have to simplify this. Simplifying that, we have y bar to be, this will give us 6x cubed minus 6x, and here will give us minus 6x cubed plus 2x, and all of that will be divided by x squared minus 1, all that squared. So okay, so having that in mind, if we further simplify, y bar will simply be, we see that this is going to cancel and we'll be left with minus 4x all over x squared minus 1, all that squared. So if we let our y, our first derivative to be 0, we're going to have, let's say negative 4x equal to 0. So x will be 0. So at the point x equal to 0, right, the function changes either from increasing to decreasing or from decreasing to increasing. Now there are many ways in which we can verify this. Let's say we have 0 here. If we take a function, let's say 1, and we insert here, 1 is not possible because it's not in our domain. Let's say 2, right? If we take 2, right, our function will be negative. All above 0 will be negative if we substitute it here, right? In fact, let's substitute in our original function. If we put 2 here, our function will be positive. So I think we have to evaluate that from the first derivative. Anyways, if we insert, I'm not exactly sure. I have to verify this. And if you're sure of that option, please you can share with me your knowledge either in the comment section or directly if you know how to get to me. So if we notice, let's take a value like 2. We notice that if we insert it here, right, we are going to have negative here, and here is always going to be positive. So above here the function is decreasing, and below, let's see what happens. Let's take a value, let's take -2. This will be positive, so positive, positive, positive. So what happens is this function is increasing from negative and decreasing from positive. So we need to have like that superficial idea of the function. So having that in mind, we are going to go to the next one. I think the next one asks if they say compute, is it decreasing, what are the local minima and the maxima, right? So we're going to go on compute and analyze the second derivative in which the interval of the function is concave or convex. So let's look at the second derivative of our function. So y prime prime of our function -4x, we'll simply use the quotient rule as well, since it's still a quotient. So again, we're going to have the denominator, the bottom, x squared minus 1, all that squared. The derivative of the top is -4 minus the top, so plus 4x. The derivative for the bottom is 2. We differentiate inside, then we copy the same function and we reduce the power by 1. All of that will be divided by x squared minus 1, all that foot, right? So y double prime will be, so to simplify this is going to be a lot. What we can do is we take x squared minus 1, that's to factor it out. We'll be left with x squared minus 1 here and -4 here, plus 4x multiplied by 4x. Yep. So this will be divided by x squared minus 1 to the power 4. So we can see that this will simplify, right? This will simplify to 3, and we can open up that to be -4 x squared plus 4, and plus 4 times 4 is 16 x squared divided by x squared minus 1, all that cube. So this is our second derivative, and we can further simplify 16x squared minus 4x squared. I think that would be 12x squared. So this will be 12x squared plus 4 divided by x squared minus 1, all that cube. Again, if we equate our second derivative to 0, it can give us an idea of what the local minima and how the function behaves. Is it concave up or concave down? By the way, if you look at this function, it is always going to be increasing, right? No matter the value of x that we choose, right? In the domain, I should specify in the domain, this function is always going to be positive. And when we know that if our second derivative is greater than 0, this is a concave, right? Concave function. And if the second derivative is less than 0, this is convex. So that's the whole idea, or this is the general information that I can draw, at least for now, based on my knowledge for this function. And the last one is sketch the function. So I'm going to sketch that in our next video, and if you're interested in seeing the sketch of this video, and do support my efforts by subscribing and liking, most importantly liking the video. And see you in the next video. Thank you very much for watching.